we've got 2 lectures. Not quite sure where we'll split in the middle, but there's sort of these 2 kind of naturally pair together, and hopefully see why at the end. So we'll just break once we've kind of got to the end of this particular topic. So this would have followed slightly more naturally on from the Kaluza-Klein theory lecture on Monday, but of course we had our snow day, so that was, I kind of talked about brains yesterday. So warp compactification is an alternate way of hiding extra dimensions. So we saw on Monday how to do Kaluza-Klein theory, where we just wrap up extra dimensions on a very small compact manifold, and nothing really, our geometry does not depend on the extra dimensions. And so what we see is that our low energy gravitational degrees of freedom, apart from 4-dimensional gravity, are a scalar, which kind of corresponds to this internal manifold changing in size, and a vector, which kind of corresponds to, well, we argued it kind of corresponds to some sort of boost prior to identification. So those were the massless degrees of freedom from the geometry. So the warp compactification is a different way of hiding extra dimensions, and we hide them by confinement rather than this process of things not depending on the extra dimension. So here the idea is that we're forcing all of our physics to happen on a submanifold, and that's how we're saying that we hide the extra dimensions. There are, there's basically 2 ways we could probe extra dimensions. We could probe them gravitationally, or we could probe them with sort of standard model physics. And so provided the extra dimensions are lower than we have checked 4-dimensional gravity works, as long as particle physics is confined, we can actually make them, relatively speaking, large. So how might this confinement work? Well, I'm just going to give you an argument that is from the 1980s by Rubakov and Shaposhnikov. It's kind of a toy model, but it illustrates some quite nice features. It sort of illustrates things about condensates, about how confinement might actually occur. So they, in the 1980s, when people were investigating these domain wall and string solutions, they sort of thought, well, what if our domain wall, or what if we lived on a domain wall in 1 extra dimension? So remember, our domain wall was a scalar field with some profile. So it was like a kink. We used the example of the kink, but you can get other kink-like solutions. All you require are disconnected vacua. So now what Rubakov and Shaposhnikov did was they coupled this scalar to a fermion, so our capital psi is the 5-dimensional fermion, the capital gammas are the 5-dimensional gamma matrices. So normally you'd expect a sort of vacuum state for this psi field to just be psi is 0. Okay, that would be the normal expectation. So because our background, this scalar field, is non-trivial, it actually sort of shifts what we mean, but yeah, by the lowest energy state.
Yeah, so sorry, during the QFT course, they told us that gamma matrices are only possible in even number of dimensions. So is there...
No, you can, all the gamma matrices are things that satisfy the anti-commutation relation. So
I might have gotten something wrong.
No, so there's definitely, so when in 5 dimensions, you just use your 4-dimensional gamma matrices, and the 5th gamma matrix is gamma 5.
Oh, okay.
So you can have spinors in any number of dimensions. The question is, what is the sort of the lowest, if you like, dimensionality of the representation? So in 4, it's whether you have, yeah?
I mixed up the dimension of the physical space and the dimension of the...
Oh, right, okay.
Sorry, I just figured out.
That's okay.
Sorry.
So are spinors still 4-component objects?
So in this case, yeah, that's right. So they still are. And it's, we're basically going to use the fact that, because gamma 5 is like our sort of 4-dimensional gamma 5, we're going to take psi to be an eigenstate. We're going to take it to be chiral under the application of the gamma 5. That's then going to give us, well, why don't I just write down? So we have... So if we just sort of thought of psi just being dependent on z, because the idea is that we've got our sort of energy density coming from the wall, which is our phi energy density, and then the sort of profile, if you like, sketching the profile of the solution, sort of has this non-trivial profile associated to the background phi field.
So is the curve in green supposed to be like the such?
Yeah, it's just meant to represent. It's the sech to the power. Obviously, how strongly localized it is would depend on the coupling G. So I've kind of assumed here that, the couplings may be slightly weaker than... So the point is, because this phi is shifting in the background, it's providing, it sort of is providing a shift of mass for the spinor. So the background of the domain wall has provided this shift in what you might think the lowest energy is for the psi profile. So we get this non-trivial profile around the wall, so we call that a condensate. But then you kind of notice, if you look at what the equation of motion is for your fermion, if you, instead of psi naught just being some constant, as long as it satisfies the massless Dirac equation, that's also a solution to the equation of motion for big psi. So that means that you've got this whole family of solutions which have this constant profile perpendicular to the wall, but can have propagating modes parallel to the wall. So you have this solution which is localized to the wall, but it's actually got, it's got some it's from the four-dimensional perspective. You don't see that profile, you just see four-dimensional massless fermion. Now, I'm not saying there are no problems with this. All I'm doing is, this is a very tangible toy model in which we see confinement. So it's just showing that in principle, it's not so daft. Now, again, from the perspective of string theory, the D-branes also have, sorry, I seem to have a cough here, also have a gauge theory confined to the brain, but that's sort of more by definition, by the way it's set up. Here we kind of see it in a more classical fashion. So this is localized, or this provides some support for the notion of localizing the particle physics, but what about gravity? So, again, after Rubakov and Shaposhnikov had written this rather fun paper, people did look into what happens to the gravitational field around one of these domain walls, and they showed, via a sort of perturbative analysis, that bizarrely enough, gravity also confines in some sense. So what I want to do is to give you a slightly more recent argument about that, which relies on what we've been doing with Gauss-Codazzi, and then we'll talk about other ways in which we could see that gravity confines. So although this was all done back in the 80s, it kind of found a new home at the beginning of this millennium via the Randall-Sundrum model, because people became interested in alternative explanations of why the gravitational constant was so big. Why is gravity so weak? And intuitively, the argument is going to be, well, gravity's weak because particle physics is confined to the brain, but gravity spills out into the extra dimensions, and that weakens it because it's somehow got to do all that work in warping the extra dimensions. So this is the complete polar opposite of Randall-Sundrum, of Kaluza-Klein. In Kaluza-Klein, nothing depends on the extra dimension in the geometry. In this compactification, Randall-Sundrum, or the warped compactification, in some sense, everything depends on the geometry. The geometry is really strongly warped in the extra dimension. You see that these profiles are very strongly suppressed in the extra dimension, and so it's the total opposite. It's completely different. So again, this is a toy model. So Randall-Sundrum put our domain wall in anti-de Sitter space. So de Sitter, we saw that when we did our domain wall, we wrote down this general metric with a warp factor. This was a more general internal metric. If we have de Sitter space, our warp factor is exponential. Remember when we had our wall in vacuum, it was like this 1 minus z over L. So here instead, it's exponentially cut off. This extra dimension is now infinite, and the brane is flat. So that is the sort of geometry or the appearance of the Randall-Sundrum domain wall. So we have this thing sitting at z equals 0. We've got this sharply peaked warp factor around it, but it has an infinite extra dimension. So again, it's this opposite to Kaluza-Klein. We have an infinite extra dimension, and at least in this background solution, the geometry depends only on z. So that's sort of totally the opposite. Kaluza-Klein's small and compact, and nothing depends on the extra dimension. So, I'm just going to write down So remember that we had the Gauss equation and the Israel equations. So this is just sort of you can go back and refer to where we derived this. So now what I want to do is I want to show you in a general way how we might get gravity, four-dimensional gravity, on this very specific sort of sharply localized solution in spite of the fact there's an infinite extra dimension. So I'm going to make for now, just two assumptions. One is simply saying that this SAB is going to be something that just is a brane tension, which we saw for the domain wall. So we have two parts of the energy momentum. If I want to convince you that we have four-dimensional gravity on the brane, what I have to do is give you four-dimensional Einstein equations, right? So I can't just sort of look at the pure brane. I want to put something on it so you can see how the internal geometry reacts to the energy momentum. I'm also going to make a simplification simply so that I'm not carrying extra baggage on this journey, but it's not required, it's not necessary. I'm going to assume that the bulk remains five-dimensional pure ADS. Now, I don't have to do that. It obviously won't, but all that it does is it just carries extra stuff. I'll tell you at the end how things change if we didn't make that assumption. So that itself means 3 reason I wanted to do that is because it just makes the 5-dimensional Ricci tensor very simple. So if you have a constant curvature geometry, what it really means is that you've only got one degree of freedom, which is the radius of curvature, so that's L. And therefore, everything else, Riemann-Ricci, has to sort of just depend on the metric with appropriately symmetrized or anti-symmetrized combinations. So the other thing that Randall-Sundrum does is have Z2 symmetry around the brane. So when I was deriving the domain wall, the kink, this sort of extended solution, I still did this. I assumed that what was on one side was a mirror image of what was on the other side. So you see the background is like that because we've got the mod Z in that warp factor. And we're just going to maintain that. We're going to assume our geometry is Z2 symmetric. So, just as a refresher, if TAB is 0, so we did this last time, I think. So Z2 symmetry essentially says that the extrinsic curvature on one side is minus the extrinsic curvature on the other side. And so our Israel equation becomes very straightforward. So the reason I just wanted to do this as a refresher was because when we last did this, we were in 4 dimensions with a 3-dimensional wall. So we had 2 over L there instead of 3 over L. So it's just to make sure that if, when you come back, you just know where that 3 came from. So now I want to keep the Z2 symmetry, keep the ADS bulk, but add in TAB. So I take the Israel equations and I sort of take the trace so I can move the delta K onto the other side, and instead of having SAB equals something, I have KAB equals something. So this is my gravitational equation coming from the Israel junction condition. So you see it splits into the background equation of motion and the perturbation when you add the TAB. Now, the eagle-eyed among you might sort of at this point be feeling uneasy because of this 1/3. Remember, what we're trying to get is Einstein gravity. So if I just put something over here, this is kind of where we're headed. So we would want that our Einstein tensor would equal 8 pi G4, where we need to figure out what G4 is, and then TAB, or RAB is 8 pi G4, TAB minus a half T. I'll put HAB here since that is our four-dimensional metric. So notice the half here. So I just want to draw attention to that. The reason being that that is the required, if you have RAB equals something, we kind of expect this should be, this sort of is indicative of a tensor structure that's a massless, sort of spin 2 massless tensor. So at the moment, although we've got something that's kind of looking promising, we've got the wrong factor, but then we've only got K here, so we're not yet sort of in trouble because we're not trying to relate it to R. So now, our strategy is going to be, instead of focusing on the Israel equations, we're going to step back to the Gauss equation. So the Gauss equation is going to, if we contract it, is going to tell us precisely about the RAB on the brain, because that's sort of from the left-hand side. It's going to be related on the right-hand side. The Riemann bit is going to give us something with 1 over L squared and factors of the metric. The extrinsic curvature is also going to give us 1 over L squareds and factors of the metric. So you can see how by following through the Gauss equation, we get something that will look like, or at least we've got a chance of getting our Einstein equation out.
Are we also going to get like G4 in terms of that G or something like that, or is that the same?
So G4 is just H because H is the first fundamental form. It's the, the induced metric on the Randall-Sundrum.
I mean the gravitational.
Oh, the G. Oh, yes. Yeah. So we'll know here this G is G5. This G has dimensions of L cubed. So we need to also find what G4 is, yeah?
Okay.
So, yeah, there's a few things that we need to do. So if we now look at our Gauss equation and contract it, what we want to make sure that we do, if we contract the Gauss equation, we still kind of get, there are sort of hidden delta functions in there because our 5-dimensional geometry has this discontinuity in the derivative of the warp factor. We don't care about those because we're taking them into account through the Israel equations. So instead of picking out the difference in the Gauss equation across the brain, so instead of sort of integrating it through the brain, instead we're going to stay on the plus side and we're going to look at what the Gauss equation becomes as we approach the brain. Or in other words, we're kind of taking an average rather than a difference across the brain. So then what we get, if we contract this equation, inputting what that 5-dimensional Riemann tensor is. So here, I've simply put in what's happening to k. So I've got my k plus. K is continuous across the, k shifts sign, but I just want to pick out what's happening on average across the brain. And for that, so even though k changes sign, obviously k squared doesn't. So those pieces are the same on each side. And so all I get is the sort of non-singular part of Riemann. So now I use the Israel equation to replace for k plus. So that's going to be a bit longer, so I'll shift boards. So I just wrote it out in full just so we can kind of see how things are going to pair up to get to what I'm going to write down next. So you see from the point of view of the empty brain, if there's no TAB, the empty brain is Minkowski, so R had better be 0. So we need the 1 over L squared terms to cancel. So if we look here, we see that we have a plus 1 over L squared from this term and that adds to that to give a 4 on L squared, and we see we're minusing that here. We see also that we get cross terms, which are essentially 4 pi g on L times either TAB or THAB. So we're also getting the first bit of the Einstein equation over here, where we've now been able to identify our G4. You have to check precisely what the fraction is by pulling all these pieces together. But then the new bit that we also get 4 pi g squared pieces. So we've also got t squared pieces. So putting it together, we get this. So you see that this is 8 pi g4 TAB minus a half t HAB plus 4 pi g squared, and we could call this extra piece tau AB, which is kind of a t squared piece. So that tells us that our Newton constant G in 4 dimensions is G over L, so that's nicely consistent by dimensional arguments, and it gives us if we were doing a perturbation expansion, this would be order t squared. And so we would say, well, that's subdominant. So to leading order, we do indeed get four-dimensional Einstein gravity. So this is very different from Kaluza-Klein. We've got an infinite extra dimension instead of a finite one. Everything's depending on it instead of being independent. But actually, we're in better shape than Kaluza-Klein theory because we haven't got this spurious scalar here. The extra dimension's kind of infinite, so it doesn't really have this breathing mode associated with it. So we really are getting four-dimensional Einstein gravity living on the brain. So the things to take away from this, which are actually common with Kaluza-Klein theory, is that the Newton's constant is not fundamental. It's now a derived quantity. And moreover, it means which I guess in other words, it means the Planck scale in 4 dimensions need not actually refer to the fundamental quantum gravity scale. Because if this L is not at the Planck scale, this kind of gives us a shift in terms of our Planck mass between 5 and 4 dimensions. So we can sort of see this heuristically. By saying, if we integrated over some extra dimension, which gives us an effective cutoff either because of the warping, so that's kind of what ADS is doing. The negative curvature is like putting yourself in a box. Or because you're in Kaluza-Klein theory and you have a finite size manifold, then we could say heuristically our Planck mass looks like the higher dimensional Planck scale times this length scale that represents the volume of the internal manifold. So we could turn us around to say that our compactification scale, therefore, is related to, this would be our Planck scale, is related to our Planck scale by this ratio of our Planck mass versus the true quantum gravity scale. So if I put in some numbers, so if n is the number of extra dimensions, and I kind of try and get some notion of a scale, I can sort of see how the scale is in sort of real units, units that we kind of have some conception of. If we compare the higher dimensional Planck scale to the TV scale, and look at, the length in centimeters. So if n is 1, then we're not really, this to sort of have a Planck scale that was close to the LHC scale, we would not really, we'd sort of have a solar system, something of that order of magnitude. But what this shows is, as you increase n, the effective scale of compactification kind of drops quite rapidly. So if n equals 6, L can be around 10 to the minus 13 centimeters, and the higher dimensional Planck scale could be a TeV, a 10 TeV. So this was why Randall and Sundrum originally explored that warped compactification model. The idea was that instead of having Kaluza-Klein theory, we have some sort of confinement mechanism. We then have a much larger internal manifold than we originally thought. And that larger internal manifold then gives us a volume factor, which takes us between the fundamental Planck scale and our four-dimensional Planck scale. So that then alters the sort of magnitude of the hierarchy problem in field theory. So that was why they originally did it. Mm-hmm.
But what about the other fields, like these fermions and all of that we study in the LHC? So their coupling constants and the renormalization process depends on the dimension.
So they would be taken to be confined to the brain. So their physics is effectively four-dimensional. Okay.
Has it been proven that there is?
Of course not. This is phenomenology.
I have a question.
Yeah.
So, okay, particles and stuff are confined into these.
Yeah.
But gravity is not, right?
Yes.
What about gravitational waves then?
Yes.
They do propagate in this extra dimension.
It depends. So that's sort of the end of this morning's story. Yeah.
I have a question for you. Sorry. I don't really understand what this compactification scale L is.
So we're being very heuristic here. So in the Randall-Sundrum is a toy model. So this is coming back also to the question about proof. I mean, to a large extent, once you actually start trying to describe something real, things get messy very quickly, and proof, really is a mathematical concept. The question is, I think it comes down to, sorry, I can see sort of giggles going on here. I think you have to be honest, about what it is, what it is you're proving. A proof requires watertight, right? And it usually requires some preconditions. And so quite typically in physics, we don't know if we've got those preconditions precisely, but what we usually say is we kind of know qualitatively what's going on, and often we make great leaps in understanding because we say, well, actually, I can't prove this, and maybe it looks a bit flaky, but if I assume something like this holds, then I get some really interesting phenomenon that explains something I see in the world. You then, having got that, you then go back and start to search for reasons why your assumption might be true, and actually quite often you find them. And so that's sort of, if you think about how quantum physics started, it was Planck doing a cookbook solution to the ultraviolet catastrophe, right? He was just like, well, assume if energy comes in packets, then this works. But at the time, he wasn't actually, at least as far as we know, seriously sort of saying this as a postulate and working it through. It was very much, we need to solve this physical problem. Here's a physical solution. It's not a proof, right? But then this led others, obviously Einstein chief among them, to come and say, well, hang on, why don't we take this seriously? It sounds a bit wacky, but let's take it seriously and let's start to see where this leads us. And so it began to put quantum theory on much more solid foundations. And of course, We've come a long way since then. But even if, even if something looks a bit sort of, shaky, if it leads you to something interesting and something that, may actually be of use, then you kind of run with it and you explore it and see where it takes you. So nowadays, so before Randall-Sundrum, string theorists would do compactifications on small Planck scale submanifolds. Now, there's a lot more interesting phenomenology going on when you try and think of effective string theory. We compactify not just on simple manifolds, but on manifolds that are warped because maybe they have rat brains. The idea of Klein, when he wanted to get rid of the scalar in Kaluza-Klein theory, saying that my extra dimension is fixed, we don't have this breathing mode, that was totally unsupportable from the perspective of the original Kaluza-Klein theory. But now we see that idea coming back in these sort of, we call it the KKLT construction, but now I'm going to miss out Katru, Kalosh, Linde, Trivedi, where they take one of these submanifolds, one of these Kähler submanifolds in string theory, and start wrapping branes. And they wrap branes precisely to stabilize certain degrees of freedom, these scalars that can wander from the Kaluza-Klein perspective. So sometimes just making some postulate that you can't prove actually leads you to something interesting, and sometime later it may be of use, or someone may figure out a way of actually doing it. So I hope that kind of sort of qualifies my, of course not, it's not proved. That doesn't mean you shouldn't do it, okay? There's a place and a time for proofs. I didn't answer a question. Damn it! I thought my politician's ruse there would answering the question I wanted to be asked. Okay.
How should I interpret this, Al?
Yeah. So I think the purpose of that shaggy dog story was that if you're compactifying on some, sort of arbitrary, shaped manifold, that has a volume. And so I'm sort of saying heuristically, if I have, say, a six-dimensional manifold that's all got, bumps and horns, it nonetheless has a volume, and that volume has a dimensionality of L to the 6. So I define, if you like, an effective length of my geometry, and that's kind of what I'm putting in here. This is the simplest thing you could do. You may have a geometry that has maybe a deformation degree of freedom, so it squishes, like, say, the S3 can squish. And so in that case, you may have a couple of length scales that characterizes your internal dimensions, so in which case you might have an L1 and an L2. You might want to have L1 close to the Planck scale and very Kaluza-Klein-y. You might want the L2 to be a bit larger and sort of to be in this. So the L is meant to be representative of the size or scale of your internal submanifold.
This is kind of like the manifold you started with before adding like this extra Z direction. So.
Well, actually, no, the L is referring to the extra dimensions. So the L is telling you, because the L comes in, if D equaled 4, there would be no L in that. L is referring to the extra dimensions.
So this is what I don't understand. Like we started by saying that this extra dimension was infinite.
In this model, yes. So up until my thought of G4 being a derived quantity, I was talking about the Randall-Sundrum model. I then said, okay, now we see that the Randall-Sundrum gives us a shift in Planck scale. Heuristically, let me think about compactifying with n extra dimensions that are not Planck scale, but L represents the scale of those extra dimensions. And then I put in, I don't want to think about complicated distortions, I just want a single scale. So it's like I've got, this or this, and that's my L. So just to kind of give a lead in, so that was this digression was in general. Let me go back to just a few comments on Randall-Sundrum, so back away from the general, and just come back to the thought on gravitational waves. What I've done, it's sort of contained in here, but so the method we've used was by Shiromizu, Maeda, and Sasaki. Give 4D effective Einstein equations. In this form, GAB is 8 pi GTAB plus order TAB squared, where there's very specific terms which are sort of you get from what's written up there. But the extra piece you get, sorry, let me make my indices add up, is a projection of the 5D Weyl tensor. So EAB I take the 5-dimensional Weyl tensor, so that's really sort of getting rid of all the Ricci stuff from the Riemann tensor, and I project it onto the brain. And so if I had perturbations in the bulk, here is where they would appear. So I had a question about gravitational waves. Now, it's partly covered in here because a gravitational wave would just be a solution to GAB equals 0. But then the only problem with this is that this is not a closed system. So EAB is unknown from this perspective. Okay? So it's a non-perturbative relation, so it's not, if you put the TAB squared pieces in, you're not actually forgetting about anything. This is true beyond just linear order. However, you don't know what that might do for you. So this is saying that if you do anything to the bulk, that also can have an effect on the brain. So how might you deal with that? So what I want to sort of come back to is thinking about so if we want to think about just your standard notion of a gravitational wave as in a perturbative solution, then I could, instead of doing this process, which is actually a bit more sort of complete, although unfinished, is I could think about making a small shift to the whole setup. So here is our background setup with our wall at z equals 0, ADS in the bulk, and of course Z2 symmetry on the brain. If I perturb this, I might imagine bending my wall and sort of adding stuff going on in the bulk. So I could, in principle, think of two ways of changing my system. So in other words, the wall can move. And the bulk can also have some sort of stuff going on. So that would be a general perturbation. And so how might we describe that? We can always write this, that we can always split our metric up into a proper distance, at least within some, range, moving away from the wall. So how does this notion of choosing this gauge, proper distance, it's called this way of writing the metric is called Gaussian normal. How does that match up to having a sort of slightly rippled wall and a rippled bulk? How do I sort of make those two pictures coincide? And then how do I actually deal with these perturbations? So in other words, what we're going to have to do is develop gravitational perturbation theory and find out what's involved in that. Because this is gravity, we're going to have to worry about issues of gauge. We're going to have to get an equation of motion for those perturbations, and then we're going to have to compare that to the equation of motion that we would have for Einstein perturbations to see whether these perturbations really are, our gravitational waves, so to speak, really are four-dimensional, or do we have other degrees of freedom? So my shaggy dog story has managed to spin this out into a reasonable lecture's length, so we're going to have a break now, and then the second part is where we'll actually talk about gravitational perturbation theory and derive the Lechnerovich operator, which is the curved space wave operator for spin 2 particles.